In this video, we're going to go over elimination reactions and how to predict products and draw mechanisms for elimination reactions. Now, previously we had talked about substitution reactions with SN1 and SN2 and how my oxygen here could be a nucleophile, attack my electrophile, and bromine leaves, and I've essentially substituted a bromine group for an alcohol group. But what also happens in lab is if you perform this reaction, not only do you get the substitution product, but you get what's called the elimination product. And what an elimination reaction does is a leaving group leaves and a double bond is formed. So we actually get a mixture of products. And we have our alpha carbon, that's where the electrophile is. But the carbon next to the alpha carbon is going to be called a beta carbon. And in an elimination reaction, it's going to feel kind of similar to an acid-base reaction where the beta hydrogen is going to be attacked. So one of these H's is attacked. And here's what happens is my nucleophile comes in, takes just the hydrogen. These electrons fall back and create a double bond, and the leaving group leaves. Okay, and so it seems very complicated because there's 3 sets of arrows, but like most organic reactions, once you get the arrows down, it should be good to go. Now, we're going to talk about major and minor products, but before we do that, we need to talk about alkenes and their stability. It is the more substituted the alkene is, so more substituted alkene is going to be more stable. Okay, so if we are talking about R groups or just groups that are not hydrogen coming off of our alkene, mono-substituted would have 1 group, di-substituted would have 2 groups, tri-substituted would have 3 groups, and then of course tetra-substituted would have 4 groups, and that's the max that you could have coming off of a double bond area. Okay, so let's place, oh, and one thing that's, I didn't type here, but that I want to say is that internal alkenes, so that would be something like that, are more stable than terminal alkenes. Okay, and that would look something like this. Oops. Okay, so that's just good information to know so we can answer this next question. So, the more substituted we are, the more stable, and then internal alkenes are more stable than terminal alkenes. So what I want to do is I want to go through and I want to think about the 2 carbons involved in the double bond and figure out what is their substitution. Are they mono, di, tri, or tetra? I think this first one is tetra. This second one is di. This third one is di. This fourth one is di. And then this 5th one is tri. So I think this guy's 1, this guy is 2. All of these are di, so I think the internal one will be 3, and then let's just call them both 4, or 4/5, whatever you want to label it as. In this video, we're going to skip E and Z alkenes. Okay, so I'm just going to skip that here. We're going to move on to notes 10, and we're going to talk about how elimination reactions work. So we're going to remove a hydrogen and a leaving group. And in their place, we're going to form a double bond. Okay, so here's how this works. Is we want to find our negative. Our negative is always going to be next to a positive like sodium. And if it's going to be elimination reactions, here's what we're going to do. Is we're going to look at, if this is the alpha carbon, we're going to look at the beta carbon. Okay, and we're going to draw in the H's on the beta carbons. Okay, oops. That top beta carbon has no H's, so we can ignore that. And what's going to happen is my nucleophile is going to come in and just take an H. The electrons then in that bond are going to fold and create a double bond. But this carbon cannot have any more bonds because it already has 4, and so the leaving group leaves. Okay, so that's how the set of reaction arrows looks. And so what we're going to do is we're going to get a double bond there plus sodium bromide. Okay, that is that product. Now, in this second one, same sort of thing. We're going to do an elimination reaction. We look at our beta carbons. This beta carbon has 3 hydrogens. This second beta carbon has none. Okay, so we don't need to worry about that. The nucleophile comes in, takes an H. The electrons from that H fall back and create a double bond, effectively kicking out your leaving group. What's left over is we have sodium bromide. Okay, now let me take this and I want to, let me do something here quickly. I want to show what if this was different. Let's say one of these methyls was hydrogen. We're still going to get, we're still going to get the product here like this. But watch what else happens. This negative can come in, take that H, those fold down. And so what we could get is this product. So if we're going to look between product number 1 and product number 2, which I'm not saying product number 2 is literally a product from how the reaction was written. I'm saying now that I have transformed that methyl into just an H, how are things different? Which one would be more stable? Well, this one is tri-substituted, where this one is mono-substituted. Also, this one is internal, so this would be called a major product. This would be called a minor product. And a major product means maybe it's produced about 80% of the time, where this one's produced only about 20% of the time. So you're going to get some sort of mixture. Okay, so let's draw all of our elimination products expected. Circle the major products if more than one product is formed. Okay. So what I want to do is I want to identify my beta carbons. Right now I can see that I could have 2 different products. So I'll draw in my H's. And as far as your homework is concerned, I'm only going to make you draw the mechanism once. So what happens is this comes in, takes an H. Those electrons fall back towards the bond with the leaving group, and the leaving group leaves. So there's one product. The other possible product that we could have is with this second hydrogen. We take off that hydrogen, electrons fall back, and bromine leaves. And right now I've just realized that I forgot something on all of them, but it's not going to be a big deal, I promise. We get sodium bromide. That's a very common product. And I bet some of you while watching this were wondering, what happens to this OH? It gains an H. We also form water, HOH or H2O, however you want to write this. And the same is true up here. And here, we got H2. Because it was H, it gained an H, we got H2. So that's my bad for forgetting that. Understand, though, when you go to college and you learn about these, whatever's above the arrow is typically just a reactant that we don't really care what it turns into, but it's something that we need. What we tend to care about is our organic reactant. Okay, so which one is more stable here? This would be my major product. This one would be my minor. Why? This is tri-substituted, where this one is only di-substituted. Okay, the more substituted, the more stable. Now, we have one more. This is called potassium tert butoxide. That's just what this is called. And as far as the test goes, I'm not going to be upset if you get this one wrong, but I'm just going to talk about it with what is true, even though you might forget. This is called, in very real sense, like most organic chemistry people talk about this as a big, bulky base. Even though it's drawn not huge, it really is a big compound because all of these have H's, and so it really is a big base. And so what happens is we have an H here and an H here that we can take off. And when you use potassium tert butoxide, which is what this is called, what would normally be a major product ends up being minor. And what would normally be minor ends up major. Okay, and we'll talk about why. So if you get that wrong on a test, I'm not going to count off any points here, but in college they definitely would. Okay, so our two products is we have a negative. I can come in, take that H, electrons fall back, kick out bromine. And then what we could also have is we could take off this H, electrons fall back, leaving group leaves. Now, this would typically be major because it's tri-substituted. We saw that above, but it's not. This is going to be minor, and this is going to be major. And here's why. It all comes down to steric hindrance. And steric hindrance refers to the ability or the lack of ability of a molecule to react due to a crowded area. Since my potassium tert butoxide is very chunky, it finds it difficult to enter this small space, where down here it has plenty of space to enter. And so because of that, it's going to react down here way more frequently because there's very little hindrance when compared to up here. Now, last thing here is you might have a question. What if we get, let's say we had, actually, let me just think just for a second, and then I'll be done. What if we could have a double bond there versus here? Let's say they were both di-substituted. Which one would be major and which one would be minor? They'd probably be 50-50. So you wouldn't actually have a major minor if a case like that arises. Those are kind of rare, but I could imagine a situation where the two products that you produce, or the three products on your homework, I know you have one where you could produce 3 different products where they could all be equivalent. That doesn't happen a lot, but it could happen.